so PS 12 is coming due, and then the final will be a week from Wednesday. We'll do a review in class on Tuesday. There is a sample midterm is on the course schedule at the moment. Sample final, rather. So you can take a look at that. We'll talk about that Tuesday as well. Any questions or problems about anything?
In
Yes?
PS 12.1, it's asking to reduce the shortest path problem to the longest path problem.
Right.
So is it essentially just asking how would you translate G, U, V, and D so that it's inputs into the shortest path problem?
Right, so, okay, so 12.1 is he's asking, 12.1, we're reducing the shortest path problem. This is the general shortest path problem where you're allowed negative, arbitrary negative cycles, degradation. Reducing that to the longest path problem. And yeah, it's a bunch of multiple choice questions, I think. Maybe some short answers, I don't remember. But yeah, you're defining two things. One is that reduction that takes input intended for the shortest path problem and turns it into input for the longest path problem, so that you can take the output of the longest path problem and convert it into a solution for the shortest path problem. So you're defining both ends of both the conversion in and the conversion out. Yep. And 12.2 is the same sort of thing. You're reducing subset sum problem to bin packing. And again, this is a more free-form question. You sort of get an idea of what the type of problem is like. Look at 12.1. But again, you're taking input intended for the subset sum problem, converting it into a bin packing instance, and then assuming that the bin pack, once you get a solution for the bin packing instance, you explain how you would turn it back into subset sum solution. Yeah.
So on the bin packing one, do you have any hints as to like the intuition for the reduction from subset sum to that?
No, it's the other way around. I don't know. Maybe I misheard you. You're reducing from subset sum to bin packing.
Yeah, so to reduce subset sum to bin.
Okay. I'll give you all the same hint I've given anyone that's asked, and that is the bin packing problem is really more general than the subset sum problem. In that with the subset sum problem, you got a bunch of numbers. In the bin packing problem, you got a bunch of two-dimensional numbers, width and a height. Just worry about bins and packages whose width is 1. Okay? Okay? And so you can do the reduction subject to that. You don't have to because you're doing the reduction to bin packing. You don't have to use the full power of bin packing problem. You can assume that everything's width 1. Okay. Any other questions? Okay. Let's continue with what we were doing last time. We were talking about this, coping with NP-complete problems. And I mentioned last time some approaches you could take. So one approach would be exhaustive search with intelligent backtracking for solving search problems. And we looked in depth at an example of doing that with 3SAT. Another is exhaustive search with branch and bound for optimization problems. So these are similar sorts of things, except this is trying to find the best solution, this is trying to find a solution. And we looked at that in depth with the traveling salesman problem. And in fact, that's your starting point for your CADIS problems. There are also other approaches. Sometimes you can't solve a problem in full generality, but you can find efficient solutions in special cases. So you can find algorithms that are correct all the time and efficient some of the time. And turn it around, you can come up with approximation algorithms sometimes that are efficient all the time, but only approximately correct. That's kind of algorithm I use for optimization problem. You can't get a perfect answer, you get one that's close. might be good enough for your purposes. We're just going to look at more about this today. That'll be our last topic. So let's start with backtracking. So we talked about 3-SAT last time, and traditionally when I've gotten to this point of the class, I've first shown this slide and the one that follows it, and then shown the 3-SAT implementation. I thought I'd try it differently this time and show you the 3-SAT implementation, and then come back and look at this slide. So what this slide is supposed to be giving is sort of a general approach to iterative backtracking. And you can sort of contrast it with what we actually did when we did 3-SAT. So you start with some problem, P0. So P0 is going to be, in terms of 3-SAT, it's just going to be the initial problem. You've got some expression, and you've got to figure out a way to assign truth values to variables to make the expression true. So that's your initial problem. And that becomes the initial set of active subproblems, this P0. And then you enter a loop, and as long as there are any subproblems to consider, this is what you do. You choose one of the subproblems. Right? Now, how do we choose what subproblem to work on then? First of all, do we even really have a set of subproblems? I'll let you think about that for a minute. We'll come back to it. Okay, so we choose some subproblem to expand. Initially, you're just choosing the one that's in the set. It has to be S0. And then you expand it into smaller subproblems. So what does that mean in terms of 3-SAT? I think that's easier to see. What are how do you expand a problem into a subproblem?
That when you set one to true and then remove all.
Okay. So we had something we're working on. We said, okay, let's assume the variable is true. We'll pick some variable and assume it's true. Or assume that it's false. So that's two subproblems. There's the case, you consider the case where the variable is true, and you simplify the problem to a new subproblem. There's the case where you assume the variable is false, and that gives you another subproblem. So there's those two cases to consider. So that's what the expand means. Also, as part of expanding, we had to pick which variable to expand. So there's actually some choice in how you do the expansion. Which variable do you pick? And we saw that matters quite a bit. Okay, and then for each of the subproblems that you generate, you look at it, and first you see if you're done. So you test it, and you do some quick tests to see if that subproblem indicates that you've completely solved the problem. In the case of 3-SAT, that means all the clauses have shown to be true. If that's the case, you just halt and report a solution. If you test it and you find out there's no way to succeed, which would be the case if you found that one of the clauses in there is false, you discard that subproblem. You don't consider it further. Otherwise, it goes into the set. So basically, looking at each subproblem you generate and quickly seeing if it's a win or a loss or unknown. And if it's unknown, you add it to the set. If it succeeds, you're done. If it fails, you just throw it away. And then you just keep iterating over subproblems. So you look at each of the subproblems, and then when that's done, your set has presumably gotten bigger, may have gotten smaller. You repeat from the top. And if this loop ever ends, you've gone through every subproblem and you failed, so you report there's no solution. So the things highlighted in yellow, we got to decide how to choose which subproblem to expand next. To expand, we have to have some way of taking a problem and simplifying it into possible subproblems. And we have to have some way of testing if we found a solution or that we're stuck and there is no solution or neither give up. So how does the 3-SAT example that we looked at last time fit into this scheme? What's similar and what's different? We didn't have a set, right? So the set in this description, this set is supposed to be keeping track of subproblems. So where's the set hiding? Yeah. Okay. So essentially, he said the stack, and the point is, what we did wasn't. This is sort of a general form of iterative backtracking. what we did was recursive backtracking. And let me show you the difference, and then we can understand what's going on. So let's start by looking how the SAT example would look like if we did it iterative, if we did it according to that strategy. So we pick a subproblem, there's only one. We turn it into its two subproblems. So now think of the fringe of the tree up here is going to be the set of items that we have. So if we were implementing it this way, we would have a priority queue perhaps that would contain those two bottom elements in it. We test them both to see if we're done, and we're not. We quickly decide that neither of those is obviously true, neither is obviously false. And then we pick one to work on. So we have to have some criteria to decide, do we work on the one, there are only two to choose from. Do we work on that one or do we work on the other one? Which do we expand next? And we didn't worry about that with recursive backtracking. What did we do? How did we decide what to expand next? Yeah?
Wasn't it just arbitrary? We just picked the next.
Yeah, well, we picked, so we had a subproblem, and first thing we would do is we would expand the one where, so we would pick some variable to expand and call it true, and work on that subproblem, and then when that didn't pan out, we would try to set the variable to false. So the recursion decided a fixed order in which to consider the subproblems. So we didn't have to worry about which one to pick, it just sort of got picked for us. So we got to pick one to expand. Let's say we pick that one. So again, we pick two variables to expand. We do that expansion. And when we test, we see that one on the right is, let's see. Okay, it's been satisfied. So x equals 1, so that was true. No, there, that one there. So this one we're stuck at. This one's something we discard, because that means we couldn't find any way to make that true. Okay, so now we've got in our set this one and this one. This one has been discarded, because it's a dead end. And again, the general case is going to pick from our set of two things, one to expand, for whatever reason, I'm going to go over on that side of the tree and expand. We expand into those two. Both of those are dead ends. So there's only one item left to consider. We come over here, and we hit one dead end, and we've hit two more dead ends. And so in the end, everything, the entire fringe here is a dead end. We report there's no solution. So there were 2 to the 4th possible ways to assign truth values, but we only had to look at 6 of them. And I didn't specify the way that we choose which subproblem to work on next. That would be something you'd have to fill in if you wanted to use this approach. But that's what an iterative backtracking algorithm would look like. There would have to be some set or some priority queue to contain the active subproblems, which roughly corresponds to the fringe of the tree, if you don't consider the dead ends. And over time, that set can get pretty big. And you got to have some way of picking each time which one you want to work on next, which subproblem you work on next. So that's a degree of freedom that you have that we don't have in the recursive version. So here's recursive backtracking. So we start with some problem. We recursively search for a solution and either find one or we don't. So the search is right here. Look at a problem, we test to see if we've succeeded. If it has, we return solution. If the test says we failed, we return null. Otherwise, we loop through all the ways in which the subproblem can expand and try to solve it recursively. So there's no set anymore. There's a runtime stack that's sort of keeping track of where we are in the recursion. So there is the runtime stack, but there's no set, and there's no explicit attempt to try to pick which of many subproblems to reduce first. We just do it in the natural recursive descent of the tree. So that's how we did 3-set in the code I showed you. So let's look at this example again. So recursively what we do is we say, okay, let W be false. It reduces to that. Let x be false, it reduces to that. Let y be false, it reduces to that. Let z be false, we hit a dead end. So let's back up. Let's let z be true. That didn't work out. We back up, let y be true. That didn't work out. We let x be true. That failed. Then we're back up at the base of the recursion, so we try again. Let w be true. We get there. Let z be true. We get to there. That's a dead end. We let z be true. We hit a dead end. Okay? So you see a different order in which the tree grew. So how much space did these two approaches take? How much space does this approach take? Yeah.
Has to build a stack frame for every recursive.
Okay. So we're talking about stack frames. So basically I'm asking you, how deep can the stack get? So how deep can the stack get?
You can get n elements deep.
Okay. So if they're n variables, you get n deep. You basically have one level per variable, because at each level you're sort of committing to one variable. So this is as deep as you can get. If you had 100 variables, you get 100 deep. Now, what happens if you do the other approach, sort of the recursive approach, where rather than just having a stack that grows and shrinks, you're constantly keeping track of all the active subproblems, and each time picking one. And you may hop around and pick one you've been working on for a while, and then decide to work over somewhere else for a while. How much space will that take? Where's the space consumed there?
In the set.
In the set, or it might be a priority queue. Okay, so how big can it get? We decided the recursive version is the size of the stack is proportional to the number of variables, to the depth of the recursion tree. If we go back and look at the other approach, right here, imagine that's a bigger example. If you had a partially expanded tree, and the program's not really representing this tree in any way. The trees help us understand what the program is doing. But how big would the priority queue be, the set be that's holding the subproblems? Initially, it contained one item. Next, it contained two items. Next, it contained these three, actually these 1, 2, 3 items. How big can it get? Yeah.
At biggest, it would be 2 to the n minus 1, right?
Okay, so where'd you get the 2 to the n minus 1?
That's from binary search trees. The leaf nodes at the bottom will be the most.
Okay, right. So basically, the size of the set is at worst proportional to the fringe of the tree, the size of the fringe of the tree. Although the tree is just conceptual, but as the search proceeds, we're essentially exploring the tree, although we're not explicitly building it. And at any given point, the elements on the fringe are the ones that are in the set, except for the dead ends that you hit. That's why I'm being a little bit wishy-washy. But if we sort of ignore the dead ends, the size of the set will be the size of the fringe of the tree. So that always bothers me, that the recursive version, the depth is the number of variables. And with the iterative version, the size of the set is proportional to 2 to the number of variables. That doesn't sound like a very good deal, an exponential amount of space to deal with variables. And in fact, my experience with trying to implement something like 3-sat iteratively like this, using a priority queue, is that the priority queue very quickly just gets too big to manage. There are just too many subproblems. Yeah?
So why is it 2 to the n minus 1 instead of just 2 to the n? Because I'm thinking like the worst case is where they always could lead to true. I'm not even sure if you can build a case like that.
Well, I think the idea is if you got a tree, a binary tree, complete binary tree, you got 2 to the n things in the tree. But the fringe is half of those elements. So 2 to the n minus 1. Give or take 1. Okay, so the set gets, the set gets too big too fast. Yeah.
So it seems like the only advantage to doing it iteratively is you can eliminate certain branches at the beginning instead of having to choose them one by one, but you only have like a chance to do that.
Yeah. The advantage of the iterative one is you've got an extra degree of freedom. You can choose what subproblem to work on next. You can decide as you're, imagine if you're doing this recursively, you're working down this side of the tree. If you can somehow figure out without going all the way to the bottom that you're doomed, or very unlikely to succeed, you can abandon ship before you finish this side and just start working over there instead. But you've got to have a good way to do that. And when I tried to implement this in preset, I did not have a good way to decide when to abandon ship and move to something that might be more promising. And just my set just kept getting bigger and bigger. So if you don't have a good way of looking at a couple of complicated expressions and deciding which is the best one to expand next, there is no advantage to this. You might as well just do it in a recursive fashion. All right, so that's backtracking. So this is now branch and bound. So remember, branch and bound is what we did when we looked at the traveling salesman problem. So here again, we start with a problem, P0. So P0 in this case is going to be, in the case of traveling salesman problem, is going to be just some graph. We've got to find the shortest Hamiltonian cycle. So again, we have a set of active subproblems. We have a measure of the best solution we found so far. So it starts out as infinite. Then what we do is, sort of like the backtracking example, iterative backtracking, we pick some subproblem to expand. And we expand it into the simpler subproblems. And for each one, we look at it. If it's a complete solution, if we have found a cycle, we update best so far. So if it's better than our current value of best so far, then best so far gets smaller. Otherwise, we need a method that'll put a lower bound on the solution we're looking at. So we've got a partial solution. The subproblem is a partial solution. We put a lower bound on any eventual solution we can produce from P sub I, and that's what we spent time doing last time. And if that's less than best so far, then PI is worth considering. But if it's bigger than or equal to best so far, we just throw it away. We can't benefit from considering to look at it because it's bound. We decide it's bound to give us the worst answer than we already have. And so that's sort of the paradigm for iterative branching. So again, you've got to be able to choose a subproblem to expand next. You've got to be able to expand it, and you've got to be able to calculate a lower bound on a partial solution. A lower bound on the eventual extension of a partial solution. Now, how's this different from what we did? We didn't do iterative branch and bound, we did recursive branch and bound. So what's the difference? Yeah. Yeah, this again it has to do with this choosing and the set. So we didn't have a set of subproblems, we just had a recursion tree. It's the same difference as with depth first, with exhaustive search, depth first search. Okay, so this is the recursive version. This is more like what we did with in class last time. You start with a subproblem, you set best so far, you call optimize. Okay. So what optimize does is it looks at some solution. If it's a complete solution, you update best so far. If it is possible that it will lead to a better solution than you've seen so far, you expand it and recursively search each of the options. Otherwise, you back up and try something different. And again, it's the same trade-offs. Either you, if you have a good way to do the choose part, you can consider that. But you got to be careful because the set can become huge. If you don't have a good way of doing the choose part, you might as well do it this way. Now, I'm going to show you another way to do branch and bound on the traveling salesman problem. And this time, I'm not going to assume the graph is complete. So for the caddis problem and the code I showed you last time, we assumed the graph was complete. And this time, let's not assume the graph is complete. Let's see how we might do things. So there's my graph. And the unlabeled edges, which most of the edges don't have a label, the unlabeled edges have a weight of 1. So there's 3 edges of weight 2 and 1 edge of weight 5. And we are, this is meant to represent sort of the midpoint of an attempt to solve the traveling salesman problem in this graph that started at vertex A. And so the scheme I'm going to use is that the yellow edges are the edges we've currently connected A to B and B to C, and we're looking for a new edge to add to that. So this is the cycle that we're building. And the green edge is always going to be an edge out of A into the rest of the unvisited vertices. And that orange edge is always going to be an edge out of C into the rest of the vertices. We'll see why that's important in a second. But that's the color scheme I'm going to be using as I do the animation. Now, we've got to put a lower bound on the any eventual solution that involves going from A to B to C. So what can you say about any eventual solution that involves going from A to B to C? What would be the components? Yeah?
We'll guarantee the minimum of 2.
Okay, so it's certainly got to involve both these edges, right? So any eventual solution will have at least those two edges. In this case, it would be 3, 2, and 1. Okay, but for an arbitrary graph, if you've done A, B, and C, then eventual tour at least will have to be that long. Okay? Now, I'm also going to say that there's got to be an edge from A out that goes to some unvisited vertex. There's got to be some edge that goes from A to H, G, F, E, or D. Right? So just to be conservative, we'll say that to get a lower bound, we'll just say that we're going to add in the lightest edge that goes from A to a vertex, to an unvisited vertex. Okay? And we're going to have some edge that goes from C out to the unvisited vertices. So let's just, we'll again be conservative and say it has to be at least as big as the lightest edge from C on out. All right, so we've got A, B, and C connected. We've accounted for the way that A and C are going to connect out to the rest of the graph. How do we put a lower bound on the edges that would connect H, G, F, E, and D together? How do we put a lower bound on the remainder of the solution? Remember, after a lower bound, because if it turns out the lower bound is bigger than this so far, we can just chuck this subproblem and try another one. What was our approach last time? How do we put a lower bound on the, using the spirit of last time, how do we put a lower bound? Yeah.
See how many nodes there are left and multiply by the lightest edge.
Right, so we would say, okay, we got 1, 2, 3, 4, 5 unvisited vertices. There are going to be 4 edges required to hook them up. We've already accounted for these edges. We've accounted for the edge that hooks A up to the rest and the edge that hooks C up to the rest. So we just got to find the, well, we could just say there's 4 edges remaining. The lightest edge in the graph is 1. So those 4 edges have to add up to at least 4. So that would give us a lower bound of 3 plus, then plus 1 is 4, plus 1 is 5, and then 4 more makes 9 would be a lower bound estimate. We can do better than that. For one thing, the graph isn't complete. There may not even be a way to hook together H, G, F, E, and D. There may not be edge, for all we know, they can't be hooked up at all. So it'd be nice to find some way of taking that into account as well when we produce our lower bound estimate. Can anyone think of a way, using an algorithm we studied earlier this semester, to come up with a lower bound? Yeah.
Disjoint sets.
I hadn't thought of disjoint sets, but I won't try to go there right now. But,
Okay.
right, that's a possibility. Yeah.
Independent set?
What's that?
It had to do with separating the graphs. I can't remember what it's called. Was it independent set?
Independent set? No, that's not what I had in mind either. Yeah.
DFS?
No, well, yeah, you could do a DFS. You could do a DFS from H. You could do a depth first search starting from one of these vertices, just using those 5 vertices in the depth first search and make sure you can reach them all at least. So if you explore from H and you can't reach G, F, E, and D, then you might as well give up right now because and back up and try something else.
Is it Dijkstra's?
What's that?
Is it Dijkstra's?
The Dijkstra's is getting closer to what I had in mind. Okay, well, you'll eventually run out of algorithms to guess. Minimum spanning tree. So what would it tell us if we look for the minimum spanning tree of the part of just the vertices H, G, F, E, and D? First of all, if it found a minimum spanning tree, what would that tell us? They're all hooked up somehow. Okay, so it'd take care of that part. And why? Ultimately, what we have to find is some, not just any old way to hook up D, E, F, G, and H. We've got to find a path, like maybe D, E, F, G, H, or I don't know if there's any option at this point. Okay, we've got to find we're going to have to, when we finish doing the exploring, we're going to hook those vertices up in some order, some consecutive order. A minimum spanning tree just hooks up any old way. It doesn't have to be a path. So how does a minimum spanning tree provide a lower bound on the actual way we're going to have to hook up D, E, F, G, and H eventually? How does that give us a working lower bound? Yeah?
Just get the weight of the minimum spanning tree.
Well, the weight of the minimum spanning tree will tell you the cheapest way to hook those 5 vertices up. But it may hook them up in a way, it may hook them up into some sort of tree that can't be incorporated into a Hamiltonian cycle. Okay, so bottom line, eventually we're going to have to find some linear way to hook together D, E, F, G, and H. And I can only see 2 ways to do it. We either go H, G, F, E, D, or we go D, E, F, G, H. But either of those ways is a spanning tree, right? Any way you can find to hook up all the vertices is a spanning tree. And if we calculate the minimum spanning tree, that's certainly a lower bound on any other way to hook them all up. So whatever way our algorithm eventually decides to connect D, E, F, G, and H, it can't be cheaper than the minimum spanning tree. So that will provide our lower bound. We add together the distance A, B, C, the lightest edge from A out to the rest of the vertices, the lightest edge from C out to the rest of the vertices, and the weight of the minimum spanning tree involving the rest of the vertices. That provides a lower bound that we can use to cut off the search when the lower bound gets too big. Let's see how this looks in action. So first we're going to start searching at A. And right from A, we're saying that the lower bound is currently 8. Now, where did that 8 come from? So what are the components of the lower bound? There's the weight of the tree that we've currently constructed, which doesn't have any edges, so that's 0. Okay, we've got to have the lightest edge from one endpoint out into the rest of the tree, and the lightest edge from another endpoint out into the rest of the vertices, but there's only one. So the lightest edge out, so we got to count it twice. The lightest edge out is 1, so that's 2. And then what's the minimum spanning tree hooking up all the white vertices? Yeah.
Well, for a weight of 8, you could do A to HG, and then
Well, we're not involving H now. I'm just looking for the minimum spanning tree of the white vertices. It's going to take, what we're essentially doing is finding the minimum spanning tree of the white vertices and adding to that the cost of connecting A to it in 2 places, which is going to be at least 2. Yeah?
The smallest I see is 6.
Okay, so we found a minimum spanning tree of 6, which was, let's see if I can do it. H to G, G to D. So if we go H, D, H, G, D, C, B, E, F, that's 6. I don't think we can do any better. That's where the 8 came from. So that's our current bound. Then we go to B. So now our estimate is going to be this 2 plus 1 to get out, 1 to get out, and then the minimum spanning tree of those 6 vertices. What's the minimum spanning tree of those 6 vertices? It's the cheapest way to hook all of them up. I've got an 8. Can we do any better than 8? let's see, we can go C to D, that's 1, to G, that's 2, to H is 3. And then we're going to have to go from G to F, that's 5, and then to E, that's 6. So it looks like 6 plus 2 is 8. Unless I got it wrong, I got 10. Well, how did I screw up?
The two edges into A and B.
Oh, I forgot the edges out of A and B.
The edge from H to C is five.
So we've got, this is 2, and we got edges of length 1 out of A and B, and then a minimum spanning tree of 6. So you can see as you do this, the yellow part gets bigger and the minimum spanning tree gets smaller. So then to C, now we've got 3 plus 4 plus 5, and then the spanning tree for all those white vertices, which is apparently the same thing. And I'm just going to try to get this to an interesting place. We keep exploring, and we finally find a solution. And the solution is 11. So that's the best we've found so far. At this point, you can actually do some branch and bound. So we back up to G, and there's no other, when we get back to G, we're looking for another way out of G to an unvisited vertex, but there's not one. The one that we haven't been to before. We get back to F, there's really nothing else to look at. We go back to E, we go back to D. Now from D we can consider going to G. Okay? So what's our bound going to look like here? What's the lower bound on the eventual size of a solution that starts A, B, C, D, G? First of all, what's the sum of the edges in the yellow part? 5, 2, 3, 4, 5. The cheapest way out of G is 1. The cheapest way out of A is 1. So that's 7. And then what's the weight of the minimum spanning tree involving the white vertices? There's not one. There's no way to hook the white vertices up in the minimum spanning in any way because there's just no edge from H to any to either F or E. So basically our lower bound is infinite at this point because there isn't a solution. And so we're benefiting from searching for the minimum spanning tree because we know there's no way to hook up the white vertices. So we might as well give up at that point and back up. So we back up, we go to C and consider going to H. Hey, what's the bound going to be there? 2, 3, 8 for the yellow edges, 9, 10 for the white edges, for the cheapest edges out of the A and H. And then, doesn't even matter what the minimum spanning tree is, we're already going to be above 11. So that hits 14. That's no good, so we back up. Go to B and consider going to E. E ends up having, if you do the estimate, you get 10, so we keep going. We consider going to D, it's a 15. So we back up, we try going to F, it's a 10. Go to G, that's a 14. And we're back up to, we've sort of explored everything you can do from A to B, and the best solution we found is 11. So we would now consider going to F or H. And you see how it continues. I'll just show you how it grows. We're going to go to F next and find a bound of 8. All the way down, we find this bound of 8. And that becomes our better solution. So now 8 is the best we've seen so far. We explore out. H is a dead end. E is a 12, that's too big. F is a 13, that's too big. We try going to H, and I guess we've already seen something that's at least 8, so we're done. So what do you think of, okay, you got a question?
Yeah, my question is why are we considering all these other branches if we know that we have to start with A, B, and C?
We don't.
Oh.
We start with A. I never said. When I previous slide, I just was explaining the meaning of the colors, assuming A, B, and C have been incorporated in the tree. But when I did this example, we just started at A. And we started looking for the best solution. And in fact, the best solution does not involve A to B, it involves A to F. So the best solution is A, F, E, B, C, D, G, H, and then A. Yeah?
So if we would have started with A to F instead, we could have eliminated a bunch of evaluations.
Right. If you're lucky and you find the optimal solution early, it makes the rest of the search faster because you've cut off more.
Is there any good way to kind of predict which way to go?
That's a good question. I don't know. There's no perfect way. But there could be a good way. I mean, one way would be, say, why take that edge from A to B? It's of weight 2. Maybe instead of, I was picking the edges out of a vertex to consider in alphabetical order, maybe we should have considered them in weight order. So we would do A to F, and then A to H, and then only A to B.
Then if you do that, like F and H could both have really high weight edges out of them.
Right.
whereas B could.
In this case, it would have paid off, but other cases it wouldn't. All right, so this is a classic branch and bound approach to traveling salesman problem. I don't recommend you do it on the caddis problem, and let me tell you why. I tried it out. I coded it up. What do you think I found out?
It took longer.
It took way longer. Why? What do you think? Yeah.
Also, minimum spanning tree at every.
Yeah. I spent all my time computing sizes of minimum spanning trees. So even though I had an efficient minimum spanning tree algorithm, computing those minimum spanning trees over and over again just took a lot of time. And I thought, well, how can this be when this is a classic algorithm for doing the traveling salesman problem? And then I thought about it, and I realized I've seen papers on algorithms that don't talk just about solving the problem, but talk about solving an incremental version of the problem. So for example, let's think about incremental sorting. Suppose you have an array that's sorted already, and then someone throws a random element somewhere in the array. So the incremental problem is then or maybe someone even gives you an element. Let's say that. You've got a sorted array and someone gives you an element and says incorporate this into the sorted array so the array is still sorted. So you wouldn't just add it to the array and then sort it using quicksort, would you? Right? What would you do? You just do a binary search for where it belongs and put it there. So that's sort of an incremental sort. So imagine a traveling salesman, a minimum spanning tree algorithm, an incremental minimum spanning tree algorithm, which might be of the form, okay, assume you have solved the minimum spanning tree for some graph. And now I add another vertex and some more edges to the graph. Is there an efficient way to update the current minimum spanning tree to a new minimum spanning tree for the larger graph without just doing it all over again? Or equivalently, or another idea would be, given a solution for a graph and a minimum spanning tree you've computed, now suppose we remove a vertex in its edges. How can we efficiently convert the original solution for the original graph into a minimum spanning tree for the new graph? That's an incremental problem. Now, why would an incremental minimum spanning tree algorithm be of interest here? Yeah?
You're only searching by one vertex at a time, so the spanning tree is only going to change by one vertex each time.
Right. As the yellow part grows and the white part shrinks, each step the white part shrinks by 1. So if we previously computed, let's say we previously computed the minimum spanning tree for all those white vertices. Now we decide to go from A to F. Now we've got to compute the minimum spanning tree for all the white vertices except F. So that's that incremental problem. So yeah, if you have to start over from scratch each time and recompute the minimum spanning tree, this isn't going to pay off. But if you have a quick way of updating your previous minimum spanning tree into a new one, then it can pay off. I was never energetic enough to try that out, but clearly it would be a win because there are efficient ways to incrementally update minimum spanning trees. But it did, I used to wonder why people studied those algorithms, what was the use of them, and I realized that it's useful for situations just like this. So anyway, for the caddis problem you're doing, where the trees are complete, I doubt this approach could compete with it. One of the advantages of this approach is it'll discover quickly that you're doomed. There is no way to, the edges, the vertices can't even be connected together. That's not even an issue if the graph is complete. It can always be connected together. Okay, we talked about other ideas last time for deriving lower bounds, but this is what I was mentioning about the incremental algorithm. All right, let's take a break and we'll look at a couple more things and then we'll be done. Okay. So I mentioned sometimes there are special cases that you can solve efficiently, even though the problem is NP complete. So independent set problem, remember that's the problem of finding the largest set of vertices that are pairwise unconnected by an edge. And this says we previously seen an efficient dynamic programming algorithm that works in the graph as a tree. I didn't actually show you that, so you just have to take my word for it. That's just an example of a special case. You can solve this problem efficiently if the graph is actually a tree, but there is no known efficient solution if it's not a tree in general. Traveling salesman problem. Given a weighted graph, what is the smallest Hamiltonian cycle? That's the problem. There is an efficient approximation algorithm if the triangle inequality holds on the graph. So we're going to look at that. This is the triangle inequality. So it just says you find any three vertices that are hooked up that way in the graph, and it better be the case that A is less than or equal to B plus C. Now, what kinds of graphs would the triangle inequality hold on? What kinds would it not hold on?
It would work if there's no negative edges.
Well, no, you could have a graph with no negative edges and it's still violate this. I mean, I could just make A be 1 or 10 and B and C be 1, and that violates the inequality. So what I'm asking is what kinds of things from the real world can we be modeling that satisfy the inequality?
Or roadmap.
Okay, would satisfy the inequality? Yeah, for the most part. I mean, it's conceivable. It depends what the map contains, what the vertices are. So that could be either or. If what you're talking about is the actual distance on the surface of the Earth between points, yes, that satisfies the triangle inequality. It's always shorter, to go directly from one place to another than to go via another place. That satisfies the inequality. What's one that doesn't? Yeah.
5, 2, 2.
So let A be 5 and B and C be 2, right? That doesn't satisfy the inequality. And the example I always give is imagine that the vertices are airports and the edges are the cost of flying, the weights are the cost of flying between those airports. So you might think that, it's cheaper to fly from LA to New York, or rather from LA to New York, than it would be to fly from LA to Salt Lake to New York. But that's not always the case. Airplane fares are just crazy, and sometimes the more indirect route can be cheaper. It just depends on a lot of other factors. So if you're trying to solve the traveling salesman problem on sort of a street map of Salt Lake City, that's for the most part, and you're trying to minimize distance traveled. The triangle inequality probably holds closely enough, but if you're trying to solve it, find the cheapest way to get from one place to another by air, it wouldn't. So I'm going to show you in a way that we're going to assume the triangle inequality holds, and I'm going to show you how to find this approximation algorithm. Okay, so this isn't going to be an exact answer. It's going to be an efficient approximate solution. First step is so I'm not showing you the edges of this graph, by the way. It'd just be too complicated. Just imagine there's edges all over the place between vertices. So the first step is to find the minimum spanning tree. So let's just assume that's the minimum spanning tree right there. If there's no minimum spanning tree, there's no hope of finding a Hamiltonian cycle. The next step is to build a tour that uses each of those white edges twice. So let me show you what I mean. We'll go from H to G, so we just start somewhere. We'll go from H to G. I don't know why it says G to G. What letter did I leave out? A, B, C, D, E, F, G, H, I. Anyway, it goes from one G to the other G. Then it goes to D. When it gets stuck, it backs up to where it came from. It goes up to A, it comes back. It tries a different way out of D. It goes out of C, out of B. Back. So you end up with that situation. So we just sort of went around, sort of look at it as going around the perimeter of the minimum spanning tree. So now we have a yellow cycle, sort of cycle. Now why is that? Why are those yellow edges not a Hamiltonian cycle? Yeah, because you're right. You're not allowed to go from H to G and from G to H. You get twice as many edges as you're supposed to have in this. So we're going to do the following thing. We're going to fix up the tour. We're going to go in the tour again, but we're going to skip any vertex that we're about to revisit and instead go to the next city directly. So let's see how that works. So we'll go from H to G, that's good. From G to G, that's good. From G to D, so far so good. D to E, but now if we keep following that tour, we're going to go back to D, which you already visited. So the idea is we fix it up by skipping D and go directly to A. So that's bad, so we just do that. Now, what happened, if we knew the length of that yellow tour, what can we say about the length of the, if we knew the length of the yellow tour to A, what can we say about the length of the purple tour? It's less because of triangle inequality, right? So before we had to go from E to D to A, in this purple we can go directly to A. And if the triangle inequality holds, we found that's a shorter way. So we've improved on that yellow tour. So we go to D, we've been to D before, so go directly to C. B, F, that's no good because we've been there before. It's no good to go to C because we've been there before, or to D, or to G, or to G, so we just go back to H. So what I've shown you is that you can, we've constructed a Hamiltonian cycle, and the question, I said this is an approximate solution, and the question is how good of a solution is it? Okay, so first, are there any questions about how I got the purple edges? Yeah?
What if there is an edge from F and H?
Yeah, I guess what I'm assuming here is that the graph is complete. If there was no edge from F to H, then I guess that approximation would fail. Okay? Yeah?
What do you mean when you say complete?
An edge from every vertex to every other vertex is a complete graph. Yeah.
When you were reassigning the edge from E to something that D followed, D was pointing to C and D was also pointing to A, so how do you make that decision?
Okay, so tell me when I get back to where you're asking.
Right there. So instead of going back to D because D has been visited, you went to A, but D also points to C.
Right, but I'm sort of following the order of the yellow arrows. So from E, we went to D and then to A.
So that can't be just an arbitrary choice. You have to have no.
Yeah, we're just going to the next one in the yellow path order that we haven't visited before. Okay, so let's see how close an approximation this is. So let TSP be the cost of the optimal solution. We don't know what the optimal solution is. So just let TSP stand for that. MST is the cost of the minimum spanning tree. So the white edge is there. So MST is the sum of the weight of the white edges. We'll let the pink tour that we found, is that pink or purple? Oh well, anyway. Tour is the cost of the pink. Now, I'm saying that 2 times MST is equal to the cost of the yellow. Okay, the yellow isn't shown here. Why is that correct? MST is the white. What was yellow? That was the yellow visited, went out this edge and back. So for every white edge it had 2 edges. One went one way, one went the other. So clearly the minimum spanning tree times 2 is the cost of yellow. This says that the TSP is greater than or equal to the MST. Okay, where does that come from? Yeah.
You need at least one edge to every other element, so the optimal solution is either going to be like, if the MST was one perfect span around to each of them, then it would equal it, but otherwise you still need a path back to the start in a cycle,
Yeah.
so it'll cost more.
I mean, one of those points where I'm listening to you and I know that's a correct solution, but a correct answer, but I'm going to look at the next. I'm going to cheat and look at the rest of this. I'm having a hard time remembering why these are. Oh, yeah, the optimal solution. Why should it be greater than minimum spanning tree? It's not enough to say that there's one more edge, right? Oh, okay. Yeah.
I'm thinking if you changed any of the edges in the MST and it was shorter, then that would have been the MST.
Yeah. All right. Now I'm back to what you were saying. It's finally dawned on me. And what you're saying. Okay. TSP is the shortest cycle, right? So remove any edge from the TSP. Okay. That'll make the TSP even smaller. But what do you have left when you remove one edge from the TSP?
MST.
You have a spanning tree. Right? The spanning tree is any way to hook everything up without a cycle. So you take the traveling salesman problem solution, you remove any edge, which will make the solution smaller. It still has to be at least as big as the minimum spanning tree, because the Hamiltonian cycle minus an edge is still a spanning tree. So it can't be smaller than the minimum spanning tree. That's what you said, right? Okay. Well, I see a lot of people don't look convinced. Let me draw a picture. That's not the right place to click. Still not the right place to click. Okay, you have some vertices. You find some solution to the traveling salesman problem. That's not going to work. Okay, that's a Hamiltonian cycle. It hooks everything together. Now remove one edge. Doesn't matter which one. That makes it even smaller than the original size of the TSP. Look at what's left. Does it connect all the vertices together?
Yes.
Okay. Does it have any cycles?
Nope.
No. So that is a spanning tree. The minimum spanning tree can't be bigger than that, because the minimum spanning tree is the minimum spanning tree. So this thing, the length of this thing has to be greater than or equal to the length of the minimum spanning tree. You add the edge back, it's bigger still. So the solution to the traveling salesman problem has to be greater than or equal to the minimum spanning tree. Okay. So back to where we were. So we got that. TSP is greater than or equal to MST. Two MSTs is greater than or equal to the torr. Okay? Why is that? So remember, the torr is this pink or purple, these pink or purple edges here.
Because 2MST is the yellow pattern where you determine that.
Right. 2MST is the yellow path. So the yellow path used, every edge twice. And basically, the way we constructed the pink torr was by improving on the yellow torr. It's improving on the yellow torr. Okay. If you double the TSP, that's greater than or equal to the torr. So again, the torr is the cost of the pink. Okay. So why does that hold?
TSP is greater than or equal to MST, so
multiplying both sides of this by 2. 2 MST is 2. Anyway. And then, so in the end, what you get is that we're within a factor of 2. So the bottom line is, if you use this algorithm to solve the traveling salesman problem, when the triangle inequality holds, you're off by a factor of at most 2.
So I was thinking you could put even a tighter bound, can't you? Like, shouldn't it be at most the final edge? Well, the final edge plus MST should be greater than or equal to the solution, right?
Yeah.
Because we added A and E and A and C, which are less than MST.
Right, so I think, depending on the topography of the graph, you can do better than twice as much. But you can construct a graph that'll be off by a factor of 2 in general. Okay? So what we've got here is an approximation algorithm that is off by at most a factor of 2, which may not sound very good, but it's at least some sort of guarantee. Now, if the triangle inequality doesn't hold, you can prove that there is no approximation algorithm for the general case, unless P equals NP, in which case none of this matters. So what is the proof? It's an easy proof. How can you argue that there is no efficient way to come up with an approximate solution to the traveling salesman problem? To come within a factor of 10 or 100 or 1,000 or n or whatever. What could you do if you could come up with what good is an approximate solution to the traveling salesman problem if it's off by a factor of 1,000,000? Even if you can find it, if you can find it efficiently. What could you do with that solution? Yeah?
It is a solution.
It is a solution,
You said that it's polynomial times that you can use.
but it's a solution to what problem?
The TSP.
Well, it's an approximate solution to the TSP, but it's an exact solution to something else. Yeah?
A Hamiltonian cycle.
Hamiltonian cycle. So a bad solution, a bad solution to the traveling salesman problem, an approximate solution to the traveling salesman problem, is an exact solution to the Hamiltonian cycle problem, which is NP complete. So unless P equals NP, you can't have an algorithm that always finds an approximate solution to the traveling salesman problem, because that would allow you to solve the Hamiltonian cycle problem in polynomial time. And that's what I just said. All right, so that was algorithms that work well for some special cases. Now let's look at algorithms that always give you approximate answers, but always work efficiently. So we're going to talk about the approximation ratio. So you've got some optimization problem, A. You've got an algorithm A for an optimization problem. And the optimization ratio is just the ratio between the time it takes I to run, or it's not time, the result that A returns divided by the optimum, the result the optimum gives you, or vice versa, whichever is right. So it just depends whether it's a minimization or maximization problem, which way you're dividing. So if you've got a problem that the optimal solution is 10 and the approximation algorithm is 20, then your approximation ratio is 2. Okay, so it's just the ratio between how good you can do and how good you can do in the best, if you solved it completely versus how well you do when you approximate it. So what we want to do is find algorithms that make these approximation ratios small. So our goal is to have the ratio be 1. And they're different. There's a hierarchy. So you have problems to which no finite approximation ratio is possible. We just argued that for traveling salesman problems. Sometimes you can have a fixed lower bound, a constant, 2 in the case of traveling salesman problem, the triangle inequality. Sometimes the approximation ratio depends on the size of the problem. So you might have a ratio the size of log n. That's possible in the set cover problem. And some problems you can make the approximation ratio arbitrarily close to 1. And the knapsack problem is an example. So we'll look at a couple of those. So here's a set cover problem. Find the smallest number of sets, such of these sets S sub 1 through S sub 3, such that their union is B. So what is the answer to this? What's the smallest? So S1 and S2 take the union. Okay, so this is an NP-complete problem. There's a greedy approach that'll give you an approximation. The greedy approach says always pick the set that covers the most uncovered elements. So if you use the greedy approach here, what would it pick first?
S3.
It would pick S3 because it covers 4 uncovered elements. Now the uncovered elements are 1 and 6. So which would you pick next? Either one. Each covers 1. So you end up picking all 3. So that's an example where the greedy algorithm fails. But we could, it turns out that it always is in a factor of the log of the number of elements in the set B you can prove. So I won't prove it. I'm just giving you an example of a greedy approach that gives you an approximate solution that you can prove boundedly. It's not worse than that approximation ratio. Now, here's the knapsack problem. Now, students always ask me, I thought we saw a dynamic programming solution to the knapsack problem. Why isn't that a polynomial time solution? Because we're just filling in a table. Okay? This is the knapsack problem. So, what did our table look like? Remember, the input to the problem is elements and their values plus the size of the knapsack. Yeah?
Is this with or without repetition?
Could be either way, but I'm going to do with repetition.
Okay. Then it would be an array of the size of the variable.
All right, so it's an array. So if your knapsack is of size 100, the array would be a length 100 that you had to fill in to solve the knapsack problem with repetition. Okay? And that's the crux of the problem. It depends on the magnitude of n, of your knapsack size. So if your knapsack size is 1,000, that's 10 bits. The size of 1,000 is 10 bits. And if you add one more bit to go to 11 bits, it's now going to take 2,000. So every time you add a bit to the input size, it doubles the size of the array you're having to use internally. That's exponential. So the problem is, yeah, we came up with a dynamic programming solution, but the size of that array is exponential when you look at it in terms of the size of the input. It's exponentially larger than the length of the input. So you could give it a mere 30-bit knapsack capacity that takes a 1 billion element array. So it turns out that algorithm is exponential. So let's think about this. Suppose this was our input. So we have these weights and these values and this opacity here, and we're trying to solve the problem. It's going to be a big cache, right? The cache is going to be, this takes, some number of bits to provide this information, but the cache is going to have to be that long. And what is that? That's 3, 3, 3. So over 9 billion elements in the array. Even though that's only 31 bits or something. 33 bits. That's a big cache. How could we come up with an approximate answer using a much smaller cache in the process? How could we change the input slightly so that we get an approximate answer? Yeah.
You could mod 10,000.
Yeah, we could basically throw away some of these low order numbers. He said mod 10,000. Suppose we just divided everything by 1,000. So instead of saying this thing is 1827381, let's just say it's 1827. And let's say this is 8389. And let's say this is, we just throw away 3 digits there. Just cut everything, round everything to divide and round, solve, and then so imagine if you wouldn't have any problem doing that if all these numbers, suppose that these numbers all ended in 3 zeros, every one of these. It'd be no, we get an exact solution just by throwing away the 3 trailing zeros in every one of these numbers, solving that problem, and we would have a solution to the original problem. But they don't conveniently end in 0, so we can just truncate them all and come up with an approximate answer. So this is what we're going to do. We're going to divide the capacity and all the weights by a constant, and we're going to round the capacity down, and we're going to round the weights up. That assures us that when we came up with a solution for the simplified problem, we're going to get something that works. It may not be optimal, but it'll work for the original problem. And the values we're going to round down. So here's that. If we divide by 10 to the 5th, it looks like that. And suddenly it's a much more tractable problem. Arrays within the realm of reason. And our numbers are a lot simpler looking. And we can find a solution. And I did that. Let me show you what I found. So I took the time to solve this one and came up with this. This is the optimal solution. It involves taking no A's, 1 B, a bunch of C's, no D's, and 4 F's. And this one over here involved taking 1 A, 1,100 D's, no C's, no D's, 1 E. And it looks like a very different solution. But how could you evaluate how good it is? This one got us to a total value of that. Yeah.
Just multiply the solution back by the number you divided it.
Right. So what we're going to do is take, we'll take one of those A's. So we'll compute the value. This number is computed by taking 1 times 19 and 4 times 84. Let's compute a number by multiplying 1 by 1827381 and that number by B up there. It's just turn it back into this solution. And if you do that, you get that. So the exact solution was 806.017.307. This solution, if you apply it to this table here, is that. So it's not as good as you can do, but it's pretty close. And it turns out that if you let n grow without bound, you can find you can achieve an approximation ratio as close to 1 as you want. So it's sort of in a theoretical sense, you can come arbitrarily close to a perfect solution of polynomial time. In a practical sense, you're not going to come arbitrarily close because this only works for huge n's. Okay, so that's the story about NP completeness. We will end there, and next time we'll do a review.